Today I'm talking about energy conversion with active dipoles from the Quantum Technologies and Dark Matter Research Lab at the University of Western Australia. There are two forces involved in driving the current around a circuit: the source force per unit charge, which is only confined to the voltage source, and the electrostatic force creating the separation of charge and producing an electric field. The EMF produced is the integral of the total force per unit charge dl, and because the integral of V dl is zero, the EMF turns out to be the integral of the force per unit charge produced by the voltage source. And so that can be due to force, thermal force, maybe mechanical force, or even a Lorentz force, which will drive an EMF. So how to include external forces to Maxwell's equations? Well, engineers have been doing this for a long time, and they do it via Faraday's law, where you get effective magnetic currents, which are fictitious at a boundary. So electromotive force is the electrical action produced by a non-electrical source, and this is a device known as a transducer, which provides an EMF by converting other forms of energy into electrical energy. And the word force in this case is not used to mean forces of interaction between bodies. It's what we call a fictitious or pseudo force. So non-electrical energy sources transmit energy or force to electric charges, and that will produce an EMF per unit length, which is the same as the force per unit charge in volts per meter. It does not conform to Maxwell's equations. It's outside of Maxwell's equations, external input to the differential equations, which drives the photonic degree of freedom. There's a way to model boundary value problems known as the surface equivalence principle. If we look at Ampere's law, you can have the curl of M, which is non-zero, and that represents a permanent magnet. And if we look at Faraday's law, we can have an electret where the curl of P is non-zero. This is just straight out of Griffiths, where he models an electret. You can see the D field is similar to a B field in this case. A polarization with a non-zero curl, which manifests the fictitious magnetic current at the boundary, which drives this D field, and we have an electric field, which is in different directions inside and outside, so the integral V dot dl equals zero. So if we have an AC magnetic field, north and south poles would be oscillating up and down, and that'd be like a magnetic current, or we could use an Amperian current. Two models which give you the same thing. This is a good paper which goes into the possibilities in Maxwell's equations, including magnetic current models. We have written this paper, looks at the electrodynamics of free and bound charge electric generators using impressed sources. So if we have a free charge source, which is a current flowing up and down here, with a magnetic current boundary source, we have an enclosed current on the boundary, which could be deemed as a free charge polarization. We get charges on the top, which is just the dot product of the polarization with the normal vector, and we have this new constitutive relationship, which if you look at antenna theory, which is an AC system, biggest effect close to the source is the effective electrostatic field. The field is becoming maximum value at this boundary, which is unusual for a conductor. So how that works is because it's non-conservative, there's this fictitious magnetic current that allows that electric field to be maximum along that boundary. In the bound charge case, that's the same, where you have effective electric field maximum at the boundary. It's a way to make electric could be through strain, the crystal, which causes a polarization, which is not induced by anything electromagnetic, it's due to mechanical strain. And in this case, the curl of these are non-zero. On a perfect electric conductor, on this boundary, you can either have a magnetic current or an electric current, and for it to radiate, it has to be this magnetic current, and you have a maximum E on this boundary, which radiates out and has a near field as well. It's a surface equivalence principle where you can model anything within a boundary as an effective magnetic surface current or an electrical current. Making a dipole antenna, you have to split two pieces of conductor, which sort of makes them like a capacitor. Why V and I are out of phase. This extra dimension is not noticed if this gap is really small, and you have effectively a current flowing up and down this direction. And if you model it as current just flowing up and down, a tangential electric field is maximum at the boundary. And that has a non-zero curl that can be modeled with an effective magnetic current boundary. But what you notice is that this had to be split, and you usually put a voltage source here. Let's have a look at what happens in a dipole antenna. You have this voltage source, which with a small gap, and that's what allows this situation to happen. Relations in bound charge voltage sources or energy harvesters, which are electrets, you get this modification too, because you have this effective impressed force, which is the same as the polarization, where the force per unit charge is created to separate these charges and make an electret, is related to the impressed electric field in in this way, then we can take the curl of this, and that gives us our modification. And our effective magnetic current is due to the non-zero curl. And if we take this polarization and we look at the curl, that occurs at the boundary, and it's like magnetic current going around here. Typically, energy harvester, as we strain it, the voltage across two ends will change. And here we are converting mechanical energy to electrical energy. I want to point out this paper recently, which shows that bulk polarization could be modeled as an effective current source. And so this led to the realization that the polarization was related to a Berry phase. What we have noticed is that this is related to electric vector potential. This is a boundary value theorem. For antennas, we have an equivalent, a surface equivalence principle. And so they look like they might be related. Recently, it has been noted in trying to understand triboelectricity, which is a form of an electret. If we look at the microscopic model and apply a macroscopic model, it's noticed that the time derivative B dot dA is 0. And that's the same in all these systems. You'll notice that there is no rate of change of magnetic flux that creates this EMF. Electrons are being transported against an average electric field by a non-conservative force, and the power for this evidently comes from a motor that spins. So the standard Faraday's law for a closed system cannot be explained. It's a non-conservative system. That is the reason. The Faraday's law is modified in this sense with a forcing function added to excite a photon degree of freedom. We can show you here that if we rotate a magnet and we keep one of the poles stationary while we rotate the other pole, we have an effective magnetic current. So when we rotate a magnet and we generate electricity, there's no monopoles, no net magnetic charge. So if we have this radial charged magnet and we spin this, there is no dB to T term, yet we generate a voltage. This is like the conversion of mechanical to electrical energy. Modern polarization theory is based on the heuristic replacement of the position vector by the K derivative operator. Berry phase is considered in momentum space rather than position space. Modern polarization theory, there's this Berry phase, which instead of being the integral of A dot dL is the integral of A dot dk. This is just like a vector potential in electrodynamics, and you can define vector by the curl of this Berry connection, and that was defined as the Berry curvature. But let's have a look back at this paper where we use the magnetic current boundary source. This model allows the definition of Berry phase in position space rather than K space or momentum space. We have this electric vector potential, which we call C, and we can relate all these different fields in terms of potentials. The electric field is related by usual potentials, but our polarization, or our impressed electric field, which is external, is related by electric vector potential and the scalar potential. And this total field, which is more like a D field, is what couples to the vector potential. So C is electric vector potential. It's a macroscopic description of some underlying high-dimensional system. These types of forces have already been noticed in the literature, and they're called curl forces. These are non-conservative terms. Conservative, it has a scalar potential, and it's non-conservative with a vector potential, and that's not the magnetic vector potential, because that is conservative. This has to be electric vector potential. One of them is a gradient force, and the other one is a curl force. Let's go back to Maxwell's equation and our definitions of our potentials. If we substitute these potentials back into the Maxwell's equations, for these we can derive these formulas. We can choose the Coulomb gauge, not the Lorentz gauge. Outside, we will have ET equals E. The impressed field doesn't exist outside the source. Equate these two to each other. The scalar potential equals the vector potential, and that means outside the electricity generator, we can either consider it as a continuation of the vector potential inside or the scalar potential outside. Going back to this paper, we looked at cylindrical dipoles, and we concluded when we add the polarization and separate the charge, that depending on the aspect ratio, the voltage across the terminals will have partly a scalar potential component and partly vector potential component. And that's because as you separate the charges, the further away they get, electric field is suppressed. The more flat and close they are, electrical field is enhanced. If the electric field dominates your system, you have a scalar potential. If the D field dominates your system, you have a vector potential. The magnetic dipole has a magnetic Berry phase, and the active electric dipole has an electric Berry phase. Engineering systems in general non-conservative. Magnetic monopoles do not exist, but magnetic dipoles do. So let's look at a magnetic dipole. surface magnetic charge. And if we spin that, we get effective surface magnetic currents. We can calculate what they are. You will then polarize any charge this way. This is through a Lorentz force. Then you can measure the voltage from the middle to the outer, or you can see that your magnetic current is generating a voltage. And we have run this experiment in the lab. We know the angular frequency, so we know the velocity is a function of r. We can calculate the effective polarization, which is the Lorentz force, and we can calculate the magnetic current, which is just the curl of this Lorentz force per unit charge. Then we can calculate the charge through these equations. And of course, the sum must equal zero. There'll be an electric field that's created through the movement of charge. And we can measure a voltage from the middle point to the outer point, and we can calculate that voltage. I got some students to do this experiment. We can calculate the voltage from the parameters. We get exactly predicted. And from our equations, we can plot what the vector potential looks like. It's also spun a magnet radial charged. If you put a wire outside while it's spinning, it creates no voltage. But if I move a wire with respect to the magnetic field, it does. So that's one of Faraday's paradox. The wire there, there'll be no generated voltage. And that's because there's no change in magnetic field. As this spins, because it's symmetric, the magnetic field remains constant around this magnet pitch. Well, what generates the voltage, you can understand it as this moving pole on the surface. It's moving faster than one on the inner surface, which generates a net voltage. We can calculate that from calculating the magnetic currents. And it's exactly as we get. Here's a calculation of scalar potential, vector potential, and flux density. And we can calculate electric field too. Here's another example. And we can do all these calculations and we get exactly what we predicted. If there was no vector potential, then all this electric field would be screened. We modeled a cylindrical electrical dipole. In here you can see the D field and the E field, the scalar potential and the vector potential. The scalar potential drops off around the charges because the E field drops off as these charges are separated. And that's why a long skinny one will have mainly vector potential and a short flat one will have mainly scalar potential. This is all written up and explained in this paper. I'll end the talk there, and thanks for listening.